Okay, so I'll record it. There we go. Okay. All right, so. Okay, so are you back on this on the spreadsheet? You can see the spreadsheet?
Yes.
Okay, so I'm just gonna make up, the rates. Let me delete guys. Okay, I'm just gonna make up rates, So like 0.01, 0.0205, I'm just making up numbers here. 0.0311, 0.0412, oh, 04, sorry. 0.0412, and then 0.0512, something like, okay, I'm just saying that. So let me show you what happens. See how the rates it's getting faster and faster as you go down.
Mhm.
So now I'm just going to take LOG of that one. And it's going to say you want to autofill it. Sure. Autofill. Okay. So the rate's changing every time. Okay. But what's not going to change every time is the H2O2. It's like the first three, they all have the same concentration. So they all have the same log of the concentration. So here's what you want to do. You want to graph rate, log of rate versus log of H2O2, but just pick the ones. Let me see if it's a control. I'm going to try command. Yeah, there we go. So just pick the ones where it's changing in the H2O2. Don't pick the ones where the H2O2 is staying the same. So it changes from -2 to -1.69 to -1. So just pick those three. It should just be 3 points. Then you're going to insert a chart. We'll see if this works. See, okay, so it did the wrong kind of chart. We want to do what's called a scatter. So I guess maybe I can find a scatter. There's a scatter right there. Okay, so there's a scatter. There we go. So you see it, I know that it kind of messed up the third point there. You can't really see it very well, but it's down at the bottom. There's 3 points there, and that's what you want to get. You don't want to have 5 points. If you had 5 points, what would happen is 3 of them would be like a vertical line because the concentration isn't changing. And that's not looking at changes. We're looking at changes here. So I'm going to actually see if I can change this from like -2.5 to -1. Just so you can see all 3 points. There we go. So now we've got a better scale there. Okay. And then you just like highlight. I think what you do is you highlight one of them. And then you do a trend line. You click on trend line. And so that's going to give you the trend line. But the thing about the trend line is that you need to have the equation that comes from it. So let me see if I can figure out how to do this because I know I did it last time. I think it's up here, data series 1. No, that's not it. It's a weird thing, but for some reason, okay, setup, go to setup again. No, that's not it. I've got it. Customize. Oh, I'm sorry. Maybe I have to click on this. So I'm clicking on the trend line. Oh man, label. Oh, here it is. It's down right below label. See where it says label underneath it? You go to use equation. For some weird reason, you have to actually tell it to put, even though it draws the trend line, you got to tell it to put the equation. So there's trend line there. You go down to label and you go use equation. And it's good to show the R squared too. It's not as important, but it's right there. So then you can click on that.
I think that maybe it's because you are using yours on you just Googled like Excel, right? Using it on Google.
Yeah, Excel's a little different. Excel, what you do is you right click on one of the data points. So you bring your cursor over to the data point and you right click, and a little pop-up menu will show. And on that menu, one of the options is add trend line. But they don't call it, do they call it trend line? Yeah, they call it trend line. So add trend line. And then when you add the trend line, it gives you an option of showing the equation and showing the R squared.
Mhm.
And so the main thing you want to get is the equation, because the equation has the slope. So like, again, these are made up numbers, but the slope is the number that comes before X. So it's 2.8 times X. The slope is the order of the reactant. So if we were just graphing H2O2, that would be the order that goes above H2O2. So that number is the number you need.
Okay.
And the other thing I noticed about your graph is that it had a negative slope. If it has a negative slope, that would mean the order of the reactant was negative, so it should be positive. So you should get a positive slope. And then you do the same thing for the Ki. It's just that what happens with the Ki is the Ki changes when the H2O2 is not changing. So it's like, like minus 1 point, I'm just, again, making up numbers, minus 1.35, minus 1.22. And then you'll see it doesn't change anymore. See, like the last three are the same. So then what do you want to do? Well, you want to graph the log of the rate, but only the ones that are changing, the first three in this case. So then you come up, and you insert a chart. And again, for whatever reason, it goes to the wrong kind of chart. You want scatter. Okay. And then click on the point, and then you can add a trend line. Again, you right click. You click on one of the points, then you right click on Excel to get the, you can probably do it from the menus that are up. I used to use Excel, but they're charging money now. So use equation.
Really?
And then R squared. Actually, you know what? There's a 365 version you can use. I would think is for free for CUNY people. But I find it so awkward to use it. You have to log in every time, and it's like, I don't know. I don't like it. Anyways, you're going to have 3 points again, but it'll be a different 3 points than the one with H2O2. And again, you're going to get that slope out of it. So here the slope would be 0.882. So that would be the order of the reactant, and then you got it.
That okay. That's also finding the order of the reactant. I was trying to figure out how do I know.
So we're using the rate law. So rate equals K, concentration of H2O2. And then you go, okay, well, let's go to that H2O2 graph. The H2O2, the slope is 2.8. So there you go. So you come back over here and you say, oh, it would be, 2.8. And then it's times the concentration of Ki. And then you come back to the Ki graph. And the Ki graph is 0.882. So 0.82. Okay. So now you got your rate law, right? You got getting those orders tells you what the exponents are. And then once you've got the orders, you've got 5 experiments where both the concentrations, because they're calculated already. And now the orders. And you know the rate. You have like everything in here except K for 5 different experiments. So what you do is you use the spreadsheet to figure out what K is, right? So you say, look, I'll write it, like this. K is going to be the rate divided by the concentration of H2O2. I didn't do, yeah, I did. To the 2.8 times the concentration of Ki to the 0.82. Now, that's how you would calculate it. So, what you want to have is okay, well, you got rate right there. You've got, I didn't show them here, but you've got H2O2, right? You'll have that. And you'll have Ki. So you can kind of, the spreadsheet's good for that, because what you do is you go like, look, it's the rate. So it's this one divided by, and then you just make sure it's in parentheses, the concentration of H2O2 to the 2.8 times concentration of Ki. So you click on the concentration of Ki to the 0.82. Then close parentheses, and then check to make sure that makes sense. You're saying, look, E4 is the rate divided by G4, which is the concentration of H2O2, raised to the 2.8, which is our, exponent. So that's good. Times I4, which is the concentration of Ki raised to the 0.82. That's right. And then you hit return. Now it says divided by 0 because there's no numbers there, right? So I'll put in some numbers. Okay, so it's getting a little bit better. Now I'm just making numbers up. There we go. So now it did give you a number. And then you can just come down and fill in, and it's going to do all 5, right? It'll do all 5 there. And then you got it. Is that right? I guess that's right. You should get 5 values that are pretty close to each other. It looks like the first 3 are really close to each other. So what happened with the last 2? I made up the numbers, so that was the mistake. I made up the numbers. But then you can do your statistics. You can do your average of all 5 values, standard deviation of all 5 values. And then you got your statistics done too. And there you go.
Oh.
So now that we've talked about, you can watch this video, but you can also watch the video again that I posted, the second one. You're probably up to the point where you want to look at the second one that I posted.
Yeah, I'll have to rewatch those videos again. I think now that you explained it, might be a little bit easier for me.
Yeah, I think it'll make more, you'll have more context. I think the first one goes through just calculating, I don't think it gets into the graphs. The second one's the one that has the graphs. So you could look at that one, but I think then you'll have it.
And is it in the procedure that explains the activation energy?
Yeah, so the last part of the second video shows you how to do the graph for the activation energy.
Okay, kind of one of the questions was asking how to for us to calculate the activation energy.
Yeah, so you got to do that third graph. So the third graph is the natural log of K, the rate constant, versus 1 over temperature. So that's like when you look at the tables, that's getting toward the end there, right? That's like almost at the end. Oh, here, maybe I can bring this up. I don't know if you can see this one. Let me stop share. Bring that up and then share again. Is that it? Yeah, that's it. Okay. So that's this one right here, the Arrhenius plot. So it's ln of K versus, there you're going to have 5 points. It's kind of hard to see in this graph that's in this. There's 1, 2, 3, 4, 5. And this one will give you a negative slope. But what you're plotting is ln of K versus 1 over T. So in that last part, I'll come up to the different temperatures. I think it's actually down here maybe. Yeah, there we go. So you'll have like 5 temperatures. So in your data set that I gave you guys, you have 5 temperatures, you know, one of them is like 90 degrees and one of them's like 80, one of them's like at 20, and then the other ones are like 5 and 10 or something like that. So you'll have them in Kelvin. 1 over T, you just take 1 over the temperature in Kelvin. So that's your x-axis right there. And then, you know, from the rates, you calculate the rates. From that, you get the rate constant, just like I just went over, and at these different temperatures. And then you take the natural log of that. And so you'll have 5 natural logs of K. 1, you know, 5, 1 over temperature. So that's 5 points. And then, you know, then you just have the computer do the work. You do a graph of those 5 points, do a scatter graph again, scatter plot. Get the line of best fit, the trend line. We always called it line of best fit, but the software calls it a trend line. And then again, your slope, you can calculate your activation energy from that slope. So the slope I think should be in the thousands. I can't remember what the numbers work out to, but they should be pretty big. The y-intercept B is usually pretty big. It's like, you know, 10 or 20 or 30, but I think yours, it actually didn't come out. The data didn't work out to where it was that big. I think it worked out to be kind of small, but that's okay. So you're going to use the slope to find the activation energy. And then the y-intercept is going to let you find the Arrhenius constant A. So the activation energy is just, you take the negative of the slope times the gas constant R, and that gives you the activation energy. And then for the Arrhenius constant, you just take E, the exponential, and you raise it to the y-intercept. And that'll give you that right there. So you'll have those 2 values. So in that last question, or the next to last question, it says, what is the activation energy? What is the Arrhenius constant? You're just going to report your values that you got. You say, look, I did the Arrhenius graph. I did this graph. I got a slope of, you know, minus 7,000. Plugging that into minus E sub A over, I'm sorry, minus the slope times R, that gives me an activation of, you know, however many kilojoules per mole that works out to be. The y-intercept was 4.7. So the Arrhenius constant is E to the 4.7, which is, you know, whatever that works out to be.
So the Arrhenius constant is the E. You said the E is the same thing as the Y?
No, E is it's a mathematical constant. It's like 2.718 or something like that. Here, I'll show you on the calculator. Okay. So let's say you've got like, 12 and you want to use the E. You just hit e to the x. Okay. So you take your number. So your y, let's say your y-intercept is 25 and you want to find the Arrhenius constant. It's just e to the y-intercept. So you just hit e to the x. And that'll give you a big number there. Okay. If you have a small number, like if you have like 0.01 and you take e to the x, it's going to give you a number close to 1. If you have like a small number and it's negative, and you do e to the x, you'll get a number. Oops, see, it doesn't work. So e to the x for that one doesn't work. Is that right? 0.2 negative. Not a number. Huh. Seems weird. That's good. 2.7. If you do 2.718 and do e to the x, oh, that would be like e squared. Okay. 1 e to the x. 2.718. Yeah, it's like 2.718. It's a mathematical function. So when you do, we do this quite frequently, like if you are doing a graph that's natural log is the inverse function of e to the x of the exponential function.
I'll be able to work on it then. Thank you.
Cool.
So I can.
Yeah, go ahead.
Go ahead. I don't know. Maybe still. If I don't know if I have time to work with a tutor on it too.
Yeah, we'll just keep working on it. Try to, keep working, keep plugging away at it.
Okay. Would I be able to work with a tutor with it?
Yeah, absolutely.
Thank you. And then I'll be able to resubmit it when I finish.
Turn it in when you're done with it, okay?
Yes, thank you so much. I really appreciate you taking time to explain it.
No problem. In order for me to get the video link to you, you know what I might be able to do? I'm gonna actually no, I think it's on my computer. But that's okay. So you only need it for a day or two. So I'm gonna upload it to YouTube and then I'll send you the link to it.
Okay, no problem.
Cool. All right. Good luck with everything. Reach out to me
I
again.
have one.
Yeah, go ahead.
I have one more question. When I was taking the exam that we had, so I had one of the problems. I worked out the answer, and then, you know how Alex is like very like they want if it's sometimes if they say like significant digits, they want it in scientific notation, and if it's not in scientific notation, they'll mark it wrong.
Oh, really? So you put it in decimal notation, they wanted scientific notation?
Yeah, sometimes it'll do that. And so I realized that they wanted it in the other way. And so I was trying to like quickly like change the answer, but then I ran out of time on the test.
Oh, yeah. I mean, if you run out of time, there's not much I can do about it. What I would recommend in the future is if you feel like you're running out of time and that's happening, just put in the decimal number and then it'll mark you wrong probably, but I can go back and kind of, adjust it.
Okay.
Yeah. Yeah, that whole time thing. What I do when I take these kinds of tests is I look at the problem. I say, okay, I can do this one quickly. So I do it really quickly. And then I'm kind of saving up time. I try to save up times for the ones that are going to be more difficult, so you don't run out of time. It's, it doesn't always work. Sometimes all problems are hard, but that's what I try to do. But yeah, next time put in your best estimate of it if you feel like you're running out of time. You know what I mean?
Okay, I'll keep that in mind. Thank you so much, Professor. I really do appreciate you taking the time to explain it because I know that you're busy. So thank you.
And I know this is believe me, this is the hardest report. The other reports are not going to be as hard as this one.
Thank you.
All right. Take care.
Hey, God bless you. Have a good night.